I guess I better record, huh? So today is the 13th of September, and we're talking about separating mixtures. So what you did was a pretty straightforward separation because you had your, what had the low vaporization point? What was the substance? What was it called? The ammonium chloride. And you had two substances that had much higher vaporization points. And you had two substances that were soluble in water and one that wasn't. Well, that was easy. If you got rid of the ammonium chloride, then you had a difference in solubility. Well, look at this. I'm telling you that these things, two of them vaporize at almost the same temperature. All of them are water soluble. Is there an easy path with this information to separate A from the rest of them? No. What happens if you heat this stuff to 250? What do you have? So let's actually draw this as a flow chart, because the flow charts are pretty useful. So if I start out to, okay, remind me, I always forget this. Rectangles are things. Can I peek at your paper, Hannah? Are rectangles? Yeah, rectangles are things and ovals are actions. Okay. So I start off with A, B, and C all together. If I were to heat to 250, what do I get? Draw that for yourself, and then I'm going to draw it, and then we'll compare notes. Does yours look something like that? If you heat this to 250, you're going to end up with vapor. You're going to vaporize both A and C. Well, that's fine if you want to separate B, but what if you actually want to be able to separate A and C? You're going to have to capture that vapor. You're going to have to recondense that substance. That doesn't work. Not if we want to separate A. So right now, we don't have any characteristic that has a difference significant enough to allow us to separate A alone. What if we think outside of just water as a solvent, and we look at other solvents? So what are some other solvents that exist? Since nobody in here has ever had to wash wheel bearings, this is lost on you. Gasoline's great. Gasoline dissolves grease like nobody's business. Also happens to be flammable, carcinogenic, mutagenic, teratogenic, all that nasty stuff. But hey, it really dissolves grease. I grew up washing greasy things in gasoline. You're not supposed to do that. It's not safe. But that's what we did. So let's think about kerosene, diesel. WD-40 is a solvent. Those are solvents. Some oils are solvents. Okay, so we decided that that won't work. But alcohol, isopropyl alcohol or ethanol, either one of them, they're slightly different. They're both alcohols, but they are slightly different. Ethanol is the one that people consume. Isopropyl alcohol is the one you keep in the bathroom. If your parents were really mean when you were little, then they might have put that on your cuts, but it hurts. The hand sanitizer is jellied ethanol. Alcohol is a solvent, and some things are soluble in alcohol. So what if we say that this is not soluble in alcohol, but these two are? Do we now have a way to separate A? Yeah, we do. We've got a solubility. It's not water, but we do have a solubility difference. So how could we design a flow chart to separate out A? What would the first step in your separation process look like if you want to separate out your A first? You're thinking add alcohol and filter? That would work. That would work. Now, if you're adding alcohol and filtering, will washing down the sides of your funnel with distilled water work? No. You're going to need a wash bottle that has alcohol in it. And in a college chemistry lab, you typically have multiple wash bottles. Later in the year, I'll tell you a story about a wash bottle filled with nitric acid that I, let's say, interacted with. I think I still have the scar. But, you know, you have to pay attention to that solubility piece. So if you're using something that is, if you're using alcohol for the separation, you need to consistently use alcohol. You can't wash stuff down with water. It's not going to do it. Okay, so once we add alcohol and filter, what would we end up with? Are you imagining something like this? You have A saturated with alcohol in a filter. You've got B and C in an alcohol solution in your beaker. Now, do you have an easy way? Here's the nice thing about isopropyl alcohol or ethanol, either one of them. They evaporate at a lower temperature than water. They tend to evaporate pretty quickly. I think it's 87 Celsius, as I recall. So you don't even have to heat this stuff terribly high. If you left it out at room temperature overnight, it would probably mostly desiccate. The oven would be easy, an hour at 100, and it would all be vaporized. Okay, so getting the alcohol dried off is easy. So we're done. We're essentially done with A. We've got A separated. How would we separate B and C? This is going to be a two-step process, I'm warning you. Okay, so if we heat this to 90, now we have B and C by themselves. We have alcohol vapor. Now we're still going to have to separate B from C. But that's not so bad. That's not so bad. And we have alcohol vapor. So what would your next step be? Come up together with the next step. Okay. And I see a few of you have got it. I'm going to have to shrink. Let's see. Can I shrink just this? If we heat to 250, what do we have? We got some lonely B. C should all be vaporized. Well, you know, and yeah, 250 should do it. I'm going to say, very often we want to take it a little bit above that vaporization point. You could do something with 3 solvents. You can have physical mixtures that have multiple pathways you could use, depending on their characteristics, depending on what your end goal is. So for instance, here, if we wanted to actually capture C, if we were trying to distill C, does this do it, or is C lost to us? Did you yeah, it's lost. I mean, you didn't capture the ammonium chloride in the physical separation lab. It's gone. Went up the stack, went up the fume hood. So, you know, if we wanted to capture C, we would have to change our method. We would have to do something to capture those fumes. Maybe there's a third solvent that C is not soluble in. In that case, you can go through multiple solvent steps. Why does this matter? Who here has ever taken any pharmaceutical product? Tylenol, ibuprofen, aspirin, cough syrup, anything. You rely on the fact that some chemist somewhere made sure that that product had only the chemicals in it that are supposed to be there and no extra chemicals in it that are not supposed to be there. I had wanted to assign a reading on this. I got it into Actively Learn, but I didn't get the questions written because I just found it yesterday. But there was an outbreak, and I skimmed the article as I was getting it ready. Children's cough syrup, dexamethasone. It's a good cough suppressant. There was an outbreak in Paraguay, I want to say 5 or 6 years ago. Children were having horrible reactions to simple cough syrup. Perfectly safe, over-the-counter cough syrup. And I think some children died. Children were having brain damage. All kinds of things were going on. It was terrible. And what they found was that there were problems in the chemical processing. There were impurities in the cough syrup. There was what was called an isomer, where it's got all the same atoms, but they're arranged slightly differently. Really hard to separate those. They're called isomers. And as a result of this impurity, children were having horrible, horrible side effects. Being able to physically separate chemicals really matters in the real world. We all do, and they were saying, well, what's the difference between generic drugs and name brand drugs? In some cases, quality control in a factory. In some cases, there is no difference. All facilities that are manufacturing pharmaceuticals are supposed to keep the same standards. So this actually does matter because we count on the medication that we take being what it says it is and nothing else. Because those other chemicals that are in it can actually have really serious biological consequences. Okay, here's what we're going to do. If you are finished with your physical separations lab, you are welcome to turn it in. You will then move on to, I'm going to actually give you guys a sample problem to work on, and then I'm going to give you a separations FIP to see if you do know how to do a separation that's not just the one we did, that's got some different solvents, different boiling points. So right now, I'm going to pause this. I'll stop it actually, and I'll give you a practice problem.